So today we start a new topic, which is associative memories. And the idea is that memories can be obtained or stored via attractors. And before describing the model, I would like to give you some biological motivation. And I know that I will be describing experiments that you've already heard about in semester Aleph, in Galit's course, but still, in the interest of those who haven't attended that course, it would be worthwhile repeating it. So I guess many of you know this lady, not personally, but because you know who she is. And some years ago, there was an interesting experiment that was done by in the lab of Yitzhak Fried, in which he looked at the neural representation of Jennifer Aniston, among other things. So the idea, how many of you have not heard about this experiment? Oh, good. So Yitzhak Fried is a neurologist working in, I think, in Tel Aviv, in Ichilov, I think, and in UCLA. And he's recording neural activity, single unit activity, from the brains of humans. The way that he does it is similar to what you do with monkeys. You put electrodes in the brains of the humans and you look at the neural activity. Now, some of you may wonder why people are willing to undergo this procedure. So the reason is that he's treating epileptic patients whose epilepsy cannot be treated by medications, and then you need surgery to remove this the focus of the epilepsy. But in order to do this, you need to know where it is, and one way of localizing the epilepsy is to put electrodes in the brain of your patient all over the place, and then wait for an epileptic seizure, and this way you can learn where it all started from. Some people are unhappy about the ethics associated with these experiments. Well, of course, then so he has people in hospital with electrodes in their brains, and then he comes to them and says and asks them whether they're willing to participate in an experiment, and of course they say yes, because who wants to argue with his neurosurgeon? And so he has many Nature and Science papers describing responses of single neuron recordings from different brain regions in response to different stimuli in the human brain. So this is the background, and this is one experiment in which the recordings were done in the posterior hippocampus.
What kind of recordings were they? I mean, what was it in their own brain? What
single unit.
Was it single unit? It was inside the real neuron, not outside.
No. This is inside single unit, same as monkeys, but with humans. Okay. So this is an example from one paper. I apologize for the quality of the image. Well, this is what you have in the paper. So what you see here is the response of a single neuron in the human brain in a region called posterior hippocampus. For the purpose of our discussion, we don't care about it, or we don't care where the posterior hippocampus is. And you see raster plots. We all discussed raster plots I think, in the first class. So there are many repetitions of presentation of this image to the patient, and you see these dots, which you can hardly see. These are the times of spikes of this neuron, and below is the histogram. So this, in this example, image number 18 was presented to the neuron. This was a 2i cell, and neurons fired a single spike in, I don't know, 5 or 10 repetitions. So the cell doesn't care much about the Eiffel Tower. Above, images 28, 30, 31, 4, 5, 29, and 32 are all different images of this lady. And the nice thing is that this neuron fired in response to this lady, presented to Jennifer Aniston, presented in various ways. It did not respond, it did not fire in response to other ladies. Okay?
This is all the same patient.
Yeah, yeah.
One patient.
Same, one patient, one neuron.
So didn't you destroy his Jennifer Aniston when you did the figure?
So the question was, did you destroy the Jennifer Aniston neuron of this patient such that he will not recognize her again? Well, no, for several reasons. Or not necessarily, I don't know. I've never met this patient, so I don't know. But no, for several reasons. One, probably no for several reasons. One is that the fact that you do extracellular recordings near the cell, you don't kill that cell. You kill cells on the way, but not this one. It's not intracellular, it's extracellular. Extracellular recording, you put an electrode near a neuron. On the way, you kill many, many neurons when you penetrate the brain in order to reach this region.
It's extracellular.
It's extracellular. No, it's all extracellular, of course. Yeah. Extracellular, sure. But still, you kill many neurons on the way. I'm sorry. This is one reason I'm so excited. Second, I cannot hold my liquor. Second reason is that this cannot be the only cell in the brain that is responsible for Jennifer Aniston, for various reasons that maybe we will discuss if you want. Yes?
He just picked a random neuron and happened to stumble upon the Jennifer Aniston one?
That's a very good point. So, the location of the electrode, according to the what the ethic committee should do is done for the purpose of identifying the locus of the seizure. They don't care about. I mean, you don't put an electrode in order to find a neuron that responds to X or Y. You put the electrode in order to identify the seizure. You happen to be near a particular neuron. And now you present a spider, a snake, and many other things, and Jennifer Aniston, and suddenly you find that this neuron responds to Jennifer Aniston and not to other things. Now, the number of stimuli, different stimuli presented to this neuron is finite. I don't know how many, maybe 100. So the fact that you find one that responds implies that probably this neuron would have also responded to other things. And that there are probably many, many neurons in the brain that respond to Jennifer Aniston. But still the representation is sparse in the sense that most neurons don't respond to most stimuli. Yes?
Did they found it in any other humans or only a single human?
I don't remember. I guess that there were several patients, but a small number. All these studies of Track-Fried, which are extremely interesting, are in some sense anecdotal, because, you know.
What are the chances to have more people with exactly the same place and the electrode?
No, I think that you place the electrodes in approximately in similar locations
That are prone to seizure.
in order to identify the seizure. But I don't know. So everything that is done by Track-Fried is in some sense anecdotal. Still, it's extremely interesting, and he's doing great things, but we all should be careful about it. Okay. Just to quantify it. So what you see here, this is a response to the different images, number of spikes in response to the different images. So most images did not elicit a single spike. Some elicited a small number of spikes. This line I think is the significance line according to something. All these are images of Jennifer Aniston. These are the colored ones. Okay? I think it's very convincing that this neuron cares about Jennifer Aniston rather than, I don't know, an oval thing in the center. It's really specific. But there are other examples. I don't remember whether this is, I'm not sure whether it's a different patient. Definitely it's a different cell in a different region. So this is Halle Berry, and this is a different region. This is right anterior hippocampus. I'm sorry?
What right in the black image? Doesn't work?
Words. Names. Of course, there is Kesher Israeli. We're all very excited about the fact that it was an image. I think it was Sharon, but no response, of course. But the interesting thing is that this neuron responded to Halle Berry in various forms. So you see a drawing of Halle Berry. Let's use this. This is just a sec. What was the question? Yeah. This is a different neuron in a different brain region. This is right anterior hippocampus. That was a neuron in a different region. But you see, these are all. It's kind of difficult to see. These are all different Halle Berries, and this is a drawing of Halle Berry. One of them is Halle Berry as a cat woman or something, which doesn't look exactly like this one. This is just the name Halle Berry. Okay? And it's not even visual, no. But I don't know if they used, well, it's visual in terms it's written Halle Berry. I don't know if they would have presented presented in an auditory, as an auditory stimulus, whether or not there would have been a response, but we don't know. And as before, all these are responses to Halle Berry, and the rest are responses to different images. And again, there is something specific here, and they write, strikingly, this cell also responds to a drawing of her, to herself dressed as a cat woman, and to the letter string Halle Berry. I think it's striking.
It's not about the image, but it's about the concept.
Exactly. There is a concept of Halle Berry that we all share, and there are neurons in our brain that are specific to some extent to this concept. Yes?
Wait, so Halle Berry was the only one that the picture has like 7 different pictures of her, or anyone like Sharon has also like 10 or 12 pictures of him in his experiment?
I don't know. I understand your question. I don't know how this was done. I guess that there was like a pre-screening stage where they presented many things and they found that it responded to Halle Berry, and then they added more pictures of Halle Berry and different controls. It's I don't remember. I can look at the paper.
But the result couldn't be related to the amount of pictures of the same person? If they showed 100 pictures of someone, wouldn't it, like,
I think it's unlikely, but we need to go back into the details and read it again in order to answer it. I don't know, but for the purpose of our discussion, I would not care much, because the point that I'm trying to make is that there is a representation of concepts in the brain, memorized concepts. Perhaps you learned it. Maybe these were naive patients that never heard about her, but they were so excited to see her in all these different forms, such that they started responding to her. This neuron started responding to her vigorously, even though he didn't know her in the first place. I think it's unlikely because, well, there's no way that they could have related the name if they were naive or something. So there's something about the memory. Questions?
But I mean, it still seems a little bit strange for me. I mean, how many image you will provide to the patient? I mean, in order to find the file that this neuron is especially for Halle-Berry.
Again, I don't know. We need to look at the details, but definitely not a huge number. So the implications are, and they write it in the paper. This is not a. They don't argue that there is a single neuron in the brain that codes for Halle-Berry, nor do they argue that this neuron responds only to Halle-Berry. That's not what they claim. I mean, this paper is often interpreted this way, but they are very clear about it. And the reason is, it's a combinatorical reason. It's extremely unlikely that you will be able to, if this neuron is responsive only to a single concept out of the many tens of thousands of different concepts that exist in the world, it's extremely unlikely that you will be able to find it in an experiment. So it's more likely that this neuron responds to several concepts, many concepts, and you bumped into one of them. Okay, so there's a representation of concepts. Now I want to show you another nice experiment from, again, from Fried. And this is now this is a different paper. In this case, this was a recording from an entorhinal cortex neuron, and the subject was presented with short video episodes. Now, I think because of copyright, they don't show these video episodes in the paper. When he presented when he presents this work in a presentation, you can actually see the videos, which is nice. And what you will see is find it. No, this cannot be.
By edge. هتعمل by edge.
by edge.
נכון, יש כאלה דברים שפתאום עובדים בזה. סייב. תשמעו אותם עכשיו, אולי ממש לא טוב. אני מוריד את זה.
Give me a second, I'll find a copy. I think I should have a copy of it somewhere. Just a sec. Apologize. Okay. But the audio doesn't work. שומעים?
אתה שומע? דמיינתי?
אתה מדמיין.
אני שומע סמדונה?
אולי זה במחשב. לא, במדיה שלנו. שלא כאילו.
לא, אני עכשיו
פה,
שומע,
משהו פה, משהו
אני
פה.
לא שומע את זה מהמחשב שלי.
משהו פה לכתוב.
לא, כי אני לא שומע את זה מהמחשב שלי. זה היה זה, הייתי שומע את זה מהמחשב. לא. אני לא מחובר. לא חיברתי.
שומע את זה מהמחשב?
אני לא שומע את זה מהמחשב.
איך הם פה ב-HDMI לוקח לנו כל כן, אתה חובר ב-HDMI וזה מסנן את הכל.
לא, אני לא שומע את זה, זה מהמחשב שלי.
שים לב, יש מיקרופון?
זה לא במחשב
הנה
שלי.
מיקרופון.
מחשב לא, זה מה שומע.
במחשב אפשר לשמוע את זה.
לא שומעים כלום.
כן, שנייה אחת.
אני בינתיים מדבר פה.
אין אודיו בסרטון.
היה אודיו.
זה סרטון שירדנו עכשיו או ש...
מה זה? שלנו גם קופצים. לא,
הבעיה היא לא הכבל, הבעיה שאני לא שומע את זה במחשב שלי. דווקא נבדוק את זה
ברגע שלהם מצאים של HDMI זה לא מעביר את הסאונד.
גם אם אני לא מחובר.
כן, צריך להגיד מה מהתאים, כאילו שומרים על כל מהלך הרבה תמונה. יש את האחד שמשמש לא אז לאט לאט אתה מתכנס למה שהכי קרוב אליו. יש לך, אתה מחליט מה שאני נכנסתי כאילו לצפוי ב-9, ואז הבאתי לו איזשהו מספר, הוא לא היה בדיוק מה התקנות שלך. לאט לאט הוא מנסה כאילו לאחד מאלה, ואז בסוף הוא מתכנס לאחד מהתקנות. כן, רציתי לתחום למטה מזה.
אולי קצת הבדל בין תשמע, שם תשמע
כן, נראה לי כי מה אתה יכול
יש גם פקודה במטלב שהוא עושה לך מערך של ישראל מהמאה עם פקודה בפנים. זאת להחליף את התקרה. לא, תקריאים כאילו אימג' של תמונה ואימג' של תודה.
Okay, I will, rather than, okay, I will tell you about the results, and during the break I will try to solve this problem. I don't want to ruin this. הורדתי את זה, אני יודע.
המחשב הזה כאילו לא שלך. לא יודע, מה שהיה ראינו פה.
זה המחשב שלי. I will try to perhaps show it from this computer. I don't know if they, yeah. Actually, it's an idea. Yeah, I'll do it during the break. I don't want to waste your time. But the point is that this pattern of activity that we saw for Halle Berry and for Jennifer Aniston, you see a similar pattern of activity when you think about these concepts. Okay? So what we learn from this movie or from this result is that the pattern of activity in the brain while we think about something is similar to the pattern of activity when we actually experience it, or when we respond to an external to an external stimulus that elicits this concept. That's the point. Now we'll try to demonstrate it after the break, but what we will start doing today is to consider a model that has these properties. And this model will try to explain how associative memories can be maintained, or how the concept of attractors can help explain the idea of associative memory, and how synaptic plasticity can give rise to attractors that are related to the patterns of activity that generated these attractors. Perhaps this was a bit obscure, so we will be more precise. So the idea is that we want to structure the connectivity matrix of the network such that the dynamics will be endowed with multiple fixed points. This would be the attractors, and that these attractors would be useful in some sense for the purpose of memory. So, if we think about the dynamics of the network that is endowed with different attractors, so this is an abstract representation of the network. So the network has many dimensions. We consider a network with many neurons. Each neuron is a dimension, but we think about we think about the two-dimensional representation. We are interested in a network that has many attractors. So each point is an attractor, and each attractor is surrounded by a basin of attraction. So starting from any point here, we will reach this different attractor. And the idea is that these different attractors will correspond to the memory of different concepts. Yes.
What are the axes of this figure?
So the axis of this figure will be, so what I wanted to draw is something that is multidimensional, n-dimensional, in which every dimension is the activity of a single neuron. So I'm thinking about dynamics in an n-dimensional space, and this dynamics in the n-dimensional space have many attractors, and each attractor corresponds to a concept. This is the idea. Now, thinking about it this way, there is something very appealing. And something that is very appealing is associative nature that naturally emerges from this framework of attractors. Now, what's the meaning of associative memory? So associative memory is memory that is driven by associations. So an association would be if I tell you something like Binyamin ne. So many of you will immediately think about our leader, Benjamin Netanyahu, right? Now this is an association. I didn't say the name. I just said Binyamin Neta or Binyamin Ne, and immediately you have the image of this politician. And thinking about it in this dynamical framework, the idea is that if you start from, if the dynamics start in the vicinity of a concept, the concept in this case was Benjamin Netanyahu. If you start in the vicinity of the the concept, the dynamics will converge to the concept. And there are many, many examples that you can think about in which our memories emerge as a result of some kind of a pattern completion association, as I described previously. So the way that we think about it is, again, these are the fixed points of the dynamics. They correspond to different concepts that we remember. This associative nature of memory is something that naturally emerges from this framework. Now the question is, how can we construct a network with a desired fixed point? With a fixed point that really corresponds to the concepts that are of interest to us. Bearing in mind something that we didn't see in the movie, but that we would like. It's not sufficient to have a network with many, many fixed points. We want these fixed points to be somehow similar to the pattern of activity that emerges from the stimulus itself. So I'm sure you all remember the first time that you saw or heard Benjamin Netanyahu, right? It generated some pattern of activity in your brain. This is a concept. And now when I presented this clue saying Binyamin Neta, you remember it, and all the memories, and thinking about the example of Jennifer Aniston, we want that the pattern of activity in your brain to be in some way similar to the pattern of activity that will emerge if you will actually see him here. Okay? So I'm saying, I don't know, you think about an airplane, that there will be a similarity between the pattern of activity when you think about an airplane to the pattern of activity that will emerge if you actually see an airplane. Yes?
So doesn't that assume that once we see something for the first time, it's the less representation change that it will have like forever?
I'm sorry?
I mean, once you have a memory, you can't modify it in this settings you tell us. So if I saw you, I can't learn anything new about you anymore than the first time I put the memory of you in my mind.
Well, the idea is that if you want to change it, then the fixed point will change. So let's say that the first time you saw me, you had a very positive view about me, and then every time that you thought about me, you had like this euphoria, these fantastic feelings. But with time, you learned that I'm not that great as you thought I am. And as a result, now every time that you think about it, you feel nausea and you have different feelings. This would imply that the fixed point is now different. Okay? Now this, okay? So this would be, so the concept of me has changed. But so the question would be, how do you generate, and maybe I also physically change. So first time you saw me, I looked great, and you know, you had this image of me, and now I'm like this, and you have a different image. So again, fixed point moved.
Okay.
And the question would be,
The question would be how we do that.
how you do that? Yeah.
So, how much information do you store in one fixed point? I mean, in terms of memory.
In order to answer this question, first we need to define the model, and then we can answer this question.
What do you want?
What I want many things. One of them would be that, you know, I have many fixed points, and they will all work great, and they will be associative, and all will store a lot of information. I want many things, but I will present a model, then we can ask ourselves whether this model at least the model addresses at least some of my desires and wishes. Okay? Yes?
And don't the fixed points change anyway when you encode a new concept?
This is an interesting question that that is of intense research nowadays in neurobiology, whether the fact that you think about something, is it kind of a passive process that you extract information from existing connections, or that you have to re-encode it later. But perhaps this is a premature before presenting the model. I mean, we present the model, then we can ask whether this model makes any sense given the current neurobiological knowledge. Yes?
What's about the area between two basins of attractions in this model? Because if I don't have enough information in order to decide between two possibilities, maybe it can be stable and not to attract directly to one attractor. Biologically.
I'm not sure that I understand.
Biologically, if you say only the B of Benjamin Netanyahu,
okay,
it can be many things.
Right.
And this is a stable situation. I cannot decide.
But eventually you think.
Well, there are several possibilities. Okay, one is that I tell you B, and you immediately think, oh, BB, right? That's one possibility. Or I say B, and you think to be or not to be. Thank you. I couldn't think of anything else except BB. Right? But somebody else, yeah. So that's one possibility that you will. I will say B, and you will dynamics will converge. Again, thinking about in this framework, will converge to BB, or will converge to be or not to be, or will converge to a third possibility which I don't have a clue. That would be another, state of the brain.
Do I must go to one option? Maybe I can be in the limit.
Like between?
Yeah.
On the border? Well, this would be,
How wide is the limit? Because
perhaps we can discuss it after presenting the model. And then we can. But it's a point worthwhile discussing, and we will discuss it. And if we don't, please remind me. Okay, so that's the basic idea. So you asked me about my wishes, my wish list. I would like to have multiple memories. Another thing that I would like to have in my model is the model would be in some sense biological, or biologically plausible, at least if we think about the brain. And we're going to discuss one particular model that dominated computational neuroscience for at least a decade. I think it's an interesting model, a bit old but still interesting, and we will discuss. I'll present the model, and we will discuss the model and its limitations. The model is named after John Hopfield from Princeton. Hopfield is still alive, I think, but pretty old. Let's take a break, and I will describe it immediately after the break. I'm sorry?
המודל, הרינג מודל שעשינו בעבודה, מה היה המטרה שלו בסוף? מה רצינו להראות שהמוח יכול לעשות? אז עכשיו הוא סוציאטיבי, אז מה זה היה?
מה שהמודל עשה זה אמפליפיקציה. עושה אמפליפיקציה, זה דבר אחד.
מגביר את
הסלקטיביות בעולם החיצוני. וזה היה במוד אחד שלו. הוא מייצר אמפליפיקציה של הסלקטיביות.
מה שנכנסתי משהו, אני מגביר את המשהו הזה פשוט?
את המשהו, אבל אספקט מסוים של המשהו. אתה מגביר את האינפורמציה לאוריינטציה.
שזה ראינו בבאמפ? שהכפי של הבאמפ הוא
הבאמפ זה מקרה קיצוני, שבו גם אם האוריינטציה או המיקום של הבאמפ היא נקבע, המיקום של הבאמפ, של האמצע שלו, בעצם מספיק שיהיה לך סלקטיביות אינפיניטסימלית קטנה באינפוט, אתה תקבל את הבאמפ. כן.
זה התוצאה שלו, מה זה נותן לי?
אז רגע, זה אספקט אחד. זה אספקט אחד, ואם אתה רוצה לדבר על הביולוגיה, אז אני מסביר למה תבנית הפעילות למה תבנית הפעילות בהיעדר סטימולוס בקורטקס דומה לתבנית הפעילות עם קורטקס, עם כי בעצם יש לך באמפ. אפשר לחשוב על זה שיש לך באמפ שכל הזמן שעושה דיפוזיה לאורך העולם המצבים. בין אם יש לך, ואת הבאמפ הזה אתה תראה, בין אם יש לך אינפוט שיש פה סלקטיביות, ובין אם אין לך אינפוט שיש פה סלקטיביות. כי המודל בוחר פתרון של סלקטיביות.
בכל מקרה, גם אם היה הומוגני.
בדיוק.
יש פלקטואציה כזאת? מה זה מדמה בביולוגיה?
שבירת סימטריה.
מה זה מדמה בביולוגיה?
בריחת המשושים. יש לך משושים למרות
אבל מה שבחר זה לא בהכרח מתאר מציאות.
כן, בדיוק.
שאנחנו יוצרים איזשהו... איזה דוגמה יש לך לזה במוח האנושי? מה אנחנו עושים כזה?
איפה אתה רואה דברים כאלה?
כן, למשל.
אז הדוגמאות שאנשים מביאים, דוגמה אחת זה LSD. קודם כל, בתגובות, כשאנשים מדברים על hallucination, ויזואלי, עבוד בכל מיני חומרים, אז יש ניסיונות להסביר את זה כתנועה של איזשהו באמפ של אקטיביטי לאורך הקורטקס.
שנוצר למרות שלא היה אותו שם, כאילו לא היה שום דבר
אתה נותן את האינטרפרטציה שהיא האילוזיה. יש דברים, איזשהו מובן דומה במיגרנות. לא יודע מה היה לך אי פעם מיגרנה. מיגרנה יש לה כל מיני פיצ'ר, אחד זה כאבי ראש. אבל יש מיגרנות בלי כאב ראש.
רואים אור מהרב?
רואים, נראה משהו כזה. יש לך איזה מין נקודה כזה, איזושהי טבעת של טשטוש שמתחילה במרכז ומתקדמת. זה הראייה, נקרא אאורה או משהו כזה, מתפשטת לצדדים. זה מקומות שבהם אתה רואה את הדברים, זה סוג של אילוזיה. אפשר להסביר אותה כתבנית פעילות שמתקדמת לאורך הקורטקס. גם אתה מסתכל שוב, בחיה מורדמת, או לא חיה מורדמת, בחיה ערה, אבל בחושך, שאין אינפוט, אתה רואה תבניות פעילות שמזכירות אותן תבניות פעילות שאתה רואה בסביבה
לכאורה זה לא דבר חיובי מבחינה... הוא כאן מדמיין מאוד שאנחנו חיים.
החיובי והשלילי הוא תלוי במה בדיוק אתה רוצה מהחיים. זה לא... תנו לי למצוא אותו
רק רציתי לשאול אותך,
המערכת של הרגישות של העולם,
הבמפים האוסילציות, למה זה יכול לשמש?
מה אתה אומר?
הבמפ שמסתובב עם האוסילציות.
זה, פה יש שאלה לא בטוח שזה משמש למשהו, זה היה יותר כדי לתרגל את נושא הבמפ וכדי לתת דוגמה למה קורה כשהשרים לא עושים.
אוקיי, ויכול להיות שאני...
אבל באופן כללי אנחנו חושבים שהבנקים האלה יכולים לזוז כתגובה לאינפוט חיצוני. פה זה לא היה כתגובה לאינפוט חיצוני, אלא כתגובה להטרוגניות.
יכול להיות שאני אולי יודע איך לסדר את זה. צריך רק כלי כמניע יש לך רמקול כזה בצד בשורת תקנות? צריך כלי כמניע מניע? הרמקול ממש? כן. עכשיו פלייבק
כן, עכשיו כאילו אתה ממש רואה גם בצד ימין ואז אתה... אוקיי. אתה אומר כאילו, יכול להיות שיש לסוף אינטגרל. יכול להיות שזה כל מה
לעשות. נכון, אבל אולי שם דברים אחרים. זה אחד פלחץ, אולי יש כאילו זה משהו של המחשב עצמו שמתעסק עם זה. זה לא של המון. אחד פלחץ זה. לא, לא, עכשיו אתה מתחת למחשב חלק. אנחנו הולך.
זה בדיוק מה שאתה עושה בי. זה ממש מה שאני כן. כאילו בסוף בי, עכשיו בוא תחשב אותה. כאילו בוא תמצא את תביא עכשיו את אחד.
מה זה?
אם זה אותו אינפורמציה
זהו, זה גם מה שאני חושב. כן, לא חשבתי, כאילו, באמת לא הבנתי כזה זהו, כן, לא, לא נתניעת לזה, זה שם, טוב. לא, זה נשמע נכון, כאילו זה כן... עכשיו אנחנו בשנה השלישית, כאילו, אז לא ברור מה היה התקן ומה לא. זה לא מהרעיון של המבחן?
כן, כאילו, שנה שעברה לא הייתי ממש כאילו לבדוק את הרחמים, זה לא סביר, והעניין...
זה באמת היה יותר קל, אני לא יודע...
לא, זה ממש קל, עכשיו כאילו, תקשיב, סטודנטי שופטים, יש להם חצי התגברות זה עדיין נהדר, אני חושב שאני כאילו, אני מבגץ שמעניין דברים כדי ש... יש לי בעיות. לא קוראים לי גם...
לא, אני חושב הבעיה היחידה עם זה אולי זה שזה מונע אינטגרציה של כל החומר. כן, לא, זה באמת היה... כאילו, הפאק היחיד שם, אני חושב, אולי באמת משהו שהוא יותר כזה, העובדה שהוא לא יכול לתת כאילו קיום, כי לא הייתה לך שום דרך חומר. כאילו, יש לזה משהו שזה לגיטימי שסטודנטים קצת בינו עליו, אבל...
כן, זה גם קצת...
אבל אני חושב באמת כל זה, גם מבחנים שפאק לא נגיד ספרים, בחור פתוח, כאילו, הכל היה עטוף. ממש מכל הכיוונים.
בסדר.
סקרין, מה? זה לא רק סקרין, זה סקרין.
דברים שהם לא מתאים בעליל.
אני לא הייתי מציג את זה ככה. הייתי, מה?
בעיניי זה לא הייתי בעליל.
גם להיות המנצח וגם להיות המצוין?
יש פה conflict of interest. נכון. זה היית שומע.
לא. זה להיות שלך. אתה מראה את הספייקים או את הניתוח?
נורא יפה,
אתה לא?
זה מעבוד לכל עובד.
רגע, אתה מחובר?
אני עכשיו עושה
זה בצד של שירות. טוב, אני נמצא בעצם.
Chip. Imitators, don't let the only real one intimidate.
סאונד פה עובד, אני לא מצליח להשמיע את הסאונד בסרט. זה דבר שאני לא מבין. אתה יכול לעזור לי?
יכול לנסות. הבעיה ששלושה פיזיקאים לא הצליחו לפתור, אני לא יודע אם
למה יש מדעי המחשב, לא?
מוריד את הסיכויים שלי. זה עכשיו המחשב, כאילו...
כן, המחשב הזה. יש לו סאונד.
ומאיפה השמעת את הסאונד עכשיו של המחשב?
יוטיוב.
אולי באמת אולי הקובץ הזה הוא סאונד.
אני שמעתי את הקובץ הזה 1,000 פעם בעבר. בוא נראה בסרט השני גם, ואיזשהו נשאר משהו קובץ. QuickTime viewers.
פשוט אותו סיים לאורי, אבל יש לך את 2 שאמרו לי.
Yeah, okay.
Yeah, like also the debit card, like all the cards.
Yeah, but like it's just less time, no?
Like I was like I had to do me and also discount. Like now I just give a discount and it's good. It was very difficult to stop to lock the credit card on discount like super difficult and you can do it online and quick.
Yeah.
Like login should be so easy. There's like emergency number, you just call and like press enter. Yeah, but they take no time.
Of course they couldn't, but they never took time.
It's like
We
y'all was
really
like
made me hate them. Like,
y'all was calling them for 1 hour and they don't pick up online. And it was just very ridiculous.
שעשיתם מהמחשב שלו, הקראת?
Like
לא, במחשב הזה, בלי לחפש.
חשבתי שזה בעיה במחשב הזה.
אין סיכוי שזה משהו נכון, זה לא בעיה.
כתובת יכול להתרגם. מחשב אצלם
הורדת אותו עכשיו מחדש או שהיה לך אותו על המחשב שלו?
הורדתי אותו, תעשה
זה הכל, זה לא... איך הוא יכול? אני לא יודע.
זה לא בלתי אפשרי, אתה יודע, אבל זה יושב באתר שלך.
לא, זה מוזר, אולי זה עניינים של פורמט, אולי זה באמת בגלל שזה לא בקוויק טיים.
אם ככה, אז השני לא היה צריך לעשות.
נכון.
But it didn't engage. You know, for the station, shuttle doesn't show up.
כן, זה אותו ישר.
Takes on people in the library, yeah, right? You know where the station is for the library? Ken?
Like next to the big parking lot.
Yeah, but he also said he stopped for the
מה ההבדל בין הקבצים?
where you can take CCA for the police station, yeah?
Like touring and
Yeah, tours do it very much. It's like the shuttle, from the yeah, more than the shuttle. Yeah, I did it like one philosophy.
like 15 minutes or something. I took it.
Either the shuttle or go to 68 is also like.
זה לא קובץ. כי נפש של קובץ ישן.
I only went to their
אבל גם במחשב הזה.
אני יכול לשמוע את זה.
כנראה משהו בתוכנה.
Okay, I was unable. It's an interesting idea. יש דברים אחרים שאני מצליח לנגן, אבל לא זה ספציפי.
לא זה קובץ.
לא, זה יהרוס את זה. כלום. טוב, I apologize. Hopefully I will be able to solve it for Thursday, for Sunday. I think it has to do with Windows 10. That's my suspicion. I'm sorry?
No, I agree.
It's used to... Okay. So the model. As always, we go back to our standard model using the standard notation. Si dot is equal to minus Si plus G of Hi. For simplicity, we assume that tau is 1.
Can you not write in this color?
Not use this color? I will try. We will assume a large network. And this time we will use a different type of nonlinearity, hyperbolic tangent.
Excuse me. Could you give me some intuition or why you choose this derivation function?
Rather than
The ideal
special linear.
Yes,
I will answer in a second. Okay, I just want to.
Is it beta then?
Sorry, beta. This is a parameter, and as always, Hi is sum over J, Jij, Sj. So the question is, why use hyperbolic tangent rather than threshold linear that we used for the in the previous example? More generally, I think that the question that you may want to ask is, why use one type of nonlinearity versus another type of nonlinearity? Sometimes we discussed linear networks, and then there was no the G function was a linear function, and then we had an example where we used some form of nonlinearity which was threshold linear. Then we have another form of nonlinearity. So it's kind of arbitrary. It seems arbitrary if we use one nonlinearity or another. Every model, every time we have something different. So what are the?
Are they interchangeable?
I'm sorry?
Are they interchangeable?
Okay, so a more general question, we're trying to model things in the brain. Now, and the question is, what should we choose? What kind of functions should we choose? And there are two approaches. One would be to do something like, let's record. Let's take these cortical neurons, inject current to them, look at firing rate as a function of the input, and then plug this, plug it back into the network. That's one way of doing it. Another way of doing it would be to do something like, we discussed it, I think, in the first class, that, well, these are something like firing rate. We know that neurons in the brain fire spikes. So maybe what we should do is we take a Hodgkin-Huxley model. This is something that some of you know. For those that don't know what Hodgkin-Huxley model, this is a model that explains the generation of spikes in the brain, and how and from this model one can extract the firing rate as a function of the input, and perhaps we should take this model as a type of nonlinearity. So again, one can do measurements, one can take a more realistic model and extract from this model, reduce from this model the nonlinearity. That would be these would be two approaches. Another approach would be to say something different, which is, let's consider the simplest function that on one hand we can solve analytically, and on the other hand capture some essence of what we are interested in. For example, when we studied working memory, we were content with using linear functions. The G function was just a linear function. When we considered the example of of the bump, the ring model, we chose a threshold linear function. Well, if we would have chosen a linear function, then the behavior would have been qualitatively different. So if you remember, we considered, I would say, 3 qualitatively different regimes or behaviors in the ring model. One was amplification. And when we studied amplification, in fact, we used a linear function. The G function was linear. We used a threshold nonlinearity, but in fact, everything was linear, because H was always positive for all neurons. Okay, so why not use linear for the entire thing? Now, we didn't use linear for the entire thing because we would not have had a bump. The bump was a result of nonlinearity. In the absence of nonlinearity, what would have happened? No. In the regime where we got a bump, unstable and diverge. The dynamics would have diverged. Now, this is a biological system. It cannot diverge, right? So the nonlinearity becomes essential for understanding the behavior. So now, so we understand that in order to understand this regime, we need nonlinearity, because the divergence is important, but what kind of nonlinearity should we choose? So we chose threshold linear because it was easy. It was easy for us to solve. And it turns out that other nonlinearities would have resulted in a qualitatively similar behavior. But this is much more difficult to solve. So we chose it knowing that we need some kind of nonlinearity, and we chose the simplest nonlinearity. This was the motivation. Now here again, we will choose a form of nonlinearity which is easy to solve. And now there will be a question, okay, what will happen, for example, if the network is linear? Is the nonlinearity important at all? Maybe it's sufficient to consider linear function, maybe threshold linear. So these are questions, are legitimate questions, and we can discuss them later. The question of why, for example, it should be nonlinear rather than linear is something that we will soon understand. But it's a good question. In general, what we do is we try to be, on one hand, realistic, on the other hand, to choose function nonlinearities that we can solve analytically, and then we want the next step is always to ask: are the results? Is a specific type of nonlinearity, is it crucial? Yes.
Hi, what's your previous point that the network would diverge
if G was linear? Yes.
Didn't we say that it wouldn't diverge because J is symmetric?
No, it's either the idea is that if it's bounded, the dynamics is bounded. Okay. So this is a model. Now I would like to introduce something that I will call memory patterns. So a memory pattern is a vector. It's a vector of the size of a network. So the notation is memory pattern. The mu, the number mu, the index mu would be the index of the memory pattern. This is just a pattern of activity of all neurons in the network. P1 mu, P2 mu, to Pn mu. So this is a memory pattern. This is one memory pattern.
P related to F?
It's not. So far, it's not. This is just SI corresponds to the state of a neuron I at a particular point in time. P is a vector which assigns something to each neuron, pattern of activity to each neuron, and we will consider pi mu to be plus or minus 1. So this is a binary vector of 1s and minus 1s. So far it has nothing to do with this, except for the fact that the dimensionality of this is equal to the dimensionality of this. I'm going to make an additional assumption about the memory pattern. I'm going to assume that a memory pattern pi mu is equal to plus or minus 1 with probability 1/2. Such that the pattern of activity of different neurons within a memory pattern and of the same neuron in different memory patterns are independent. So the idea is the following. I'm generating memory patterns in the following way. I'm starting with memory pattern 1. I'm tossing an unbiased coin to determine whether the activity of the first neuron in the first memory pattern should be plus or minus 1. Then I do it for the second one. Then I do it for the third one. And I finish memory pattern 1. I go to memory. I finish the first memory pattern. Then I go to the second one, and so on. That's how I generate these memory patterns. Questions so far?
Sorry, for me, I missed something. What was plus 1 and minus 1?
So these memory patterns are binary. It's a binary vector of plus and minus 1.
Yeah, I mean.
With probability 1/2.
Yeah, I mean, what's the meaning of plus 1 and minus 1? Is there any?
We will discuss it in a second.
Oh, okay.
This is just yes.
Why the probability need equal to the half?
That's a model. That's a model. We will question. I will rephrase your question. What will happen if the probability is 0.6 or 0.1 or 0.01? Right. That's the question. That's one question you could ask. Or what would happen if
the pattern more probabilities on the other?
Oh, this would be if it's 0.6. Oh, yeah. So that's one question you could ask. What about more complicated? Maybe memory 1 is all 1s, but memory 2 is all minus 1s, or things like that. Maybe. But we will consider the simplest. And then we can ask questions about what would happen if. The last piece of this model is something about the connectivity matrix, Jij. And Jij is equal to 1 over n, sum over mu, pi mu, pj mu, for I that is not equal to j, and jii is equal to 0 when I is equal to j. So this is the model.
So every memory has its own dynamic?
So let's try and understand the intuition behind this memory pattern and behind this connectivity rule. So the way to think about it is the following. The way that I'm going to construct this network is the following. I'm going to take the first memory pattern and I'm going to impose it on the network. So this is a network. There are no good options. Okay. So this is a network. So let's say that I have a network with 4 neurons. And the first memory pattern is equal to 1, 1, 1, 1. No, let's say 1, minus 1, 1, minus 1. Let's make it more interesting. And let's say that the second memory pattern is equal to 1, 1, minus 1, minus 1. Okay, so now I'll explain how I construct this connectivity matrix. So the first step is to start with all jij being equal to 0. I'm starting with a network that is unconnected, which neurons are not connected to each other. Now I impose the first memory pattern, so I'm going to call this neuron number 1. Let's put them, draw them this way. So I'm going to, this is neuron number 1, number 2, number 3, number 4. So the first step is to impose this pattern of activity on the network using external input. I'm forgetting about this recurrent connections. I'm imposing a pattern of activity on the network, and this would be neuron 1 being active and neuron 3 being inactive. Sorry, neuron 3 being active. And now I'm going to consider all pairs in the network. So for example, let's think about the pair neuron 1 to neuron 3. Neuron 1 to neuron 3, they are both active. So the connectivity let's do it in an even simpler way. Let's say that there is only a single memory pattern with the network. So what would be the connectivity? So here we sum over all patterns, but there is no sum because there's only one pattern. So let's see what would be the connectivity here. Well, neuron 1 and neuron 3 are active. So what should be the connectivity, the strength of connectivity between them? It would be just 1 times 1. So this would be connected with a strength of 1. Well, not exactly 1 over n. And this would be 1 over n. Now, let's consider neuron 1 and neuron 2. What would be the strength of connectivity between neuron 1 and neuron 2? Well, it would be 1 times minus 1. So this would be minus 1 over n. And this would be minus 1 over n. And now we can consider, I don't know, let's say neuron 3 and neuron 4. So this would be again minus 1 over n and minus 1 over n. And there's 1 to 4 and 2 to 3 and so on. So this is how this would be the implementation of this idea in a network with one neuron. Now, what is the motivation behind this learning rule? Well, the motivation is that neurons that fire whose activity is similar will be connected with positive connections, and neurons whose activity is different will be connected with negative connections. Other questions?
So 1 means active, -1.
Maybe 1 means active and -1 means inactive. Something like this, yes. It's an abstract model. Yes?
Could you say it's like a Hebbian rule?
In some sense, it's like a Hebbian rule, in which neurons that fire together wire together. When people talk about Hebbian rule, they mean various things. Often they talk about spike timing dependent plasticity, and we don't. This is not the issue here.
Could you please repeat this calculation I missed it? Like how did you end up with -1 over n?
Between 3 and 4.
For example.
Okay, so neuron number 3 is +1, neuron number 4 is -1. J is equal to 1 over n.
Okay.
Sorry?
I thought it was like the select line.
המינוס הזה?
Yeah.
I see. Okay. Okay, so this was the case of one memory pattern. Let's say that there's another one, that there are two memory patterns. So let's say that this would be 1, 1, minus 1, minus 1. So let's consider now only the connection between neuron number 3 and number 4. So now we need to sum over two things. There will be number 3 will contribute 1 times minus 1, which is equal to minus 1. Number 4 will contribute minus 1 times minus 1, which is plus 1. So if we have this, if we have these two memory patterns, then the strength of connectivity between neuron 3 and neuron 4 would be equal to 0. So is the idea clear? The model is clear? So various things, and if we have a 7 or 23 memory pattern, we just sum over all of them. So there are several things that are worthwhile noting. One is what you mentioned is it's Hebbian-like. In some sense, it's Hebbian. That's one thing. Another is that one way of implementing this is by an incremental learning rule. So basically, the idea is similar to the process that I described, is that we start with one memory pattern, we impose it on the network, and then we make some changes, and then we impose another memory pattern, and we make some changes, and eventually we sum over all the changes. That's one. So that's thinking about the way of implementing it. And finally, and again, this is something that I guess that you will discuss in next year, is that thinking about the biology, this is a synapse. So this is a presynaptic neuron, and this is a postsynaptic neuron. This is the synapse. So the synapse, the strength of the synapse could correspond to something like the number of receptors in the postsynaptic side, or the probability of release of in the presynaptic side, things like that. Changes in the synaptic efficacy will correspond to changes to these things, and this learning rule has the property that it's a local learning rule. So changes to the synaptic strength depend only on the presynaptic and postsynaptic activities. They don't depend on things that happen in other synapses in different places in the network. So in that sense, this rule can be thought of as a biological rule because it's a local rule. Questions? Yes?
Does the initial connectivity in the brain at the beginning of the life is really zero? Because
no, I don't know no, it's definitely not equal to 0. No. We'll think about this more. Okay. Questions? So, the question that we're interested in is how are these fixed points related to, for example, to these memory patterns? That's the kind of question that one would be interested in. But first, how do we know that the dynamics here are endowed with fixed points at all. So again, we're using the same trick that we used previously. We know that connectivity, there's symmetry in the connectivity. This implies that the dynamics will converge to a fixed point. So, well, there will be fixed points. And the question that we will ask is whether these fixed points are related in any way to these patterns of activity. So, and perhaps before asking this question, I will go back to your question, okay, about the nonlinearity, about the type of nonlinearity and about this G function. So what can we say about the linear case? Let's say that G is a linear function, not a nonlinear function. What can we say about the dynamics? Well, how do you know that it will diverge? Let's say that G is equal to 0. Will it diverge? What will it converge to?
Converge.
Sorry? It will converge to SI being equal to 0. Yes?
So maybe it needs to be nonlinear, so we could go to the 1 or the -1. So if it was linear, maybe you can have these two values of a thing.
So what can we say about the case of when it's linear? So why will there be only one fixed point? I'm sorry? Why should it converge to 0 and not to 5? No, if G is equal to 0. No, now we're talking about the case of G is linear. So let's consider the case of a set of linear equations. So we consider the case of G being linear. So we have SI dot is equal to minus SI plus HI, which is sum over J of Jij Sj. Who was behind this saying that there's a single fixed point? You, yeah. Okay. So we have a set of linear equations.
N equations for n variables.
So let's consider the fixed point of this equation. So assuming that it will converge to fixed point and will not diverge, then the fixed point is SI is equal to sum over J of Jij Sj. And in general, we expect this. Sorry?
It will be all 0?
Yeah.
N variables for n equations.
So S will be 0. If it will not. Yeah. So it's kind of not interesting. This problem is not interesting in the linear case. So nonlinearity is essential for this problem to become of any interest in order to have multiple fixed points as we were interested before. This is a set of equations in the case of linear. So this is just a fixed point solution. SI dot is equal to 0, so SI is equal to sum over J of Jij Sj, a set of linear equations. N equations with n variables.
And what if this phi is no positive? It could be negative, right?
What?
This phi could be negative, right?
Yeah.
Yeah, but so in this way, if I use the threshold.
Okay, so now you're saying, but maybe if I use threshold nonlinearity, then there will be interesting things. But at least we know, perhaps, but at least we know that nonlinearity is important. Threshold linear is nonlinear. But at least we know that threshold nonlinearity is necessary in order to obtain something interesting. We will go back to the issue of nonlinearity and the type of nonlinearity here later. At least we will partially address it. Okay, but this is not a problem that we're asking. This is a problem that we're discussing, and well, this is kind of complicated. I mean, having n equations, n linear equations with n variables is nice. Having n nonlinear equations with n variables is not nice, especially in the limit of very large n. But we want to say something about the fixed points still. What can we say about the fixed points? So we will start by considering a simplified case. So we will consider a simplified case. And this simplified case is the limit of beta going to infinity. So this is, in this limit, hyperbolic tangent becomes the sine function. So now we can, this will make it easier for us to consider the fixed points of this equation. So what would be a fixed point of this equation? Well, this would be the fixed point would be SI will be equal to sine of HI. This is these are the fixed points of this set of equations. So now we need to find these fixed points. I'm sorry?
Each pattern is a fixed point?
Well, each solution. So we have a set of n equations with n variables. Sum over j, 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 f, j, if you want. So we have a set of n equations. We need to find the fixed points. So this is kind of complicated. Well, it's actually very complicated. Turned out that there will be many, many fixed points. Turns out that the number of fixed points will be exponential with the number of memory patterns, as it turns out. This is not trivial to prove, but we'll do something simpler. I'm going to ask a simpler question, which is, are the vectors P mu fixed points of the dynamics? Or what are the conditions such that Pi mu are fixed points of the dynamics? Well, the reason that I'm putting forward this question is that the answer is sometimes yes, right? I mean, this you could have imagined from the psychology of classes. Now, if this is true, this is kind of interesting, because this implies, or this is a way of implementing particular fixed points of the dynamics. This is a way of generating these desired fixed points. And remember how we generated this connectivity matrix. We imposed this pattern of activity on the network. We imposed this pattern of activity on the network, and then we used Hebbian plasticity to change the synaptic connections. Now, if these are indeed fixed points of the dynamics, if these patterns are indeed fixed points of the dynamics, we have something similar to what we wanted in the first place when talking about memory. Then we will have, when we present a particular pattern, let's say Binyamin Netanyahu, we have a particular pattern of activity in the network. And now, this pattern of activity that was imposed by the concept Binyamin Netanyahu will emerge, or may emerge, as a fixed point of the dynamics. So if I will say B, immediately this dynamics will converge to this fixed point, which corresponds to the concept of Binyamin Netanyahu. And this would be, and then if we impose another concept, which is now an airplane, the airplane will also be a fixed point. So dynamics will converge to either Binyamin Netanyahu or to an airplane, depending on the initial conditions, if both are fixed. So this is a way of imposing fixed points that have this property that the desired, that the pattern of activity in the network at the fixed point is also the pattern of activity when this concept was encoded. Questions? So this would be a fixed point. So this would be a fixed point if, or a necessary condition, necessary and sufficient condition, is that pi mu should be equal to sine of sum over j, jij, pj mu for every j. If this is true, then the vector p mu is a fixed point of these dynamics in the limit of beta going to infinity. Questions? So next week we will start from this point and we will prove that under certain conditions P mu are indeed fixed points of the dynamics, and we'll discuss these conditions. Hopefully I will be able to solve this problem with a movie and show it to you next week, but it might not be easy.